SKA is going to be 20 or 30 years. The VLT project I was working on in Chile was 20 years.
It's a very, very large telescope, isn't it?
Very large. Yeah, we don't have very good names in astronomy, as you know. Yeah. The next one after the VLT is the ELT.
Extremely large.
Extremely large telescope. Good. 10 points too.
Okay, Professor Peter Quinn, thank you very much for joining us on the Range Project tonight.
Pleasure.
Now, we're really, really excited to have you on the show because you are the current Executive Director of ICRA, involved with the Square Kilometre Array project and others.
Yep.
We need to have a bit of a shout out to your beautiful wife, Kate Quinn, who is our Director of Advancement and Philanthropy, who's in the studio with us tonight.
Wise move.
So welcome, Kate.
Thank you. Thanks for having me.
So we want to zoom in right now on exactly what's happening at ICRA, and particularly with the Square Kilometre Array and how that's developing.
So it's a particularly important time, actually. In fact, today and tomorrow, there's a meeting going on, unfortunately a virtual meeting in the current world, but a meeting of the SKA Council. Okay, and the SKA Council is the governing body of the project. They're meeting to decide to begin the project after 20 years of planning and cajoling and fighting and fundraising. It's time that we actually made a decision. Yes, we can start this project and dig the first hole and build the first thing. So that's happening today and tomorrow. So it's a very timely occasion to talk about the SKA. It has been something that's been in the minds of many people around the world for at least 20 years to be able to build a telescope that's big enough to see effectively back to the very first objects that ever formed in the universe. So that's kind of the holy grail of astronomy. We know how big it kind of has to be that sort of powerful a telescope. It has to be like 1 million square meters of collecting area to do that. And that's no mean feat. It's about 3,000 times better than anything that's ever been built before. If you look at the history of telescope builders and look at their track record, their report card, they every 20 years kind of build something that's 5 or 10 times better than the previous 20 years. Now we're asking in this one 20-year generation of telescope builders to build something 3,000 times better. That's a game changer. In fact, that factor of 3,000 is exactly the same ratio as the distance from the Earth's orbit to the moon. So 100 kilometers versus 300,000 kilometers. So it's an Apollo-like ambition. It's an Apollo-like achievement when it gets done. But it does have the ability to open up potential to discover things we've never dreamed of.
And it's happening in our backyard.
And it's happening here in West Australia's back garden. And it's happening on the time scale of the young people that are in school right now, in the years 9, 10, whatever it is. They are going to be in universities and graduating and becoming interested in science at exactly the time when this telescope first turns on.
How long was it on your radar for, so to speak, when you first heard about it and wanted to work for it, and now is your role as director? Is that correct?
Yeah. So look, it's a long story in the sense that if you became an astronomer or a researcher in Australia, when I did graduated with a PhD in the early 1980s, it was like obligatory to get kicked out of the country and go overseas and work overseas. It was, that was part of, when I first arrived at Mount Stromlo where I did my PhD, on the very first day, the director said, don't unpack, right? In 3 years' time, you're getting on a plane and you're going somewhere else, because as a researcher, to expand your horizons, you had to go and work all over the world, in Europe or America or wherever it happened to be. So I was kicked out of Australia and I spent 27 years in America and Europe and South America doing research work. Because those were the places where the big projects were running. There were no big projects in Australia in astronomy. We didn't have any high mountains. We didn't have any, attractive places to build big telescopes in some sense. So we were in Europe, and it was, we'd always wanted to come back to Australia, be part of the academic environment back here. And it was the fact that all of a sudden there was a telescope that actually wanted to be in Australia, wanted to have access to the remoteness of the West Australian desert. So I had the chance to use my interest in astronomy, my interest in big projects, and my interest in coming home all collided together in about 2005. And I applied for a position back here in Australia and got it.
So what were some of the earliest conversations you had about the Square Kilometre Array, and when it was, the birth of the idea? And
I knew about it when I was in Europe. So I was in Europe working for a big organisation in Europe doing more or less optical astronomy projects in South America mostly, which is another interesting whole story. But I knew the Square Kilometre Array was an idea. People wanted to build a very large radio telescope. So telescopes come in all sort of flavours and shapes and sizes, some that detect optical light you can see with your eyes, some that X-rays and gamma rays and things, but this was a radio telescope project. I was not a radio astronomer, I was more of an astrophysicist, to be honest with you, but I knew there was an aspiration to build this very large radio telescope because we wanted to push back our view of the universe to a very, very early point, the very first objects that were created. And it just so happens that most of the energy, most of the signals that are generated at that point in the universe arrive at the Earth in the radio part of the spectrum. So you have to build a radio telescope if you want to look at it. So I knew that was all going when I was based in Europe. I thought, that's an exciting project. I'd love to be part of it because it's going to address some of the questions that I was interested in, dark matter and dark energy and things. So then an opportunity appeared, right? So the West Australian government, the Australian Commonwealth government were keen to build new institutes in Australia to take advantage. If Australia was going to be the host, in particular West Australia was going to be the host of this project, we need institutes, we need people, we need things in Australia to basically anchor the return from that project in Australia, not just go elsewhere in the world. So I guess it was in the early 2004, 2005, 2006 when I was really started to kind of get interested in the possibility of being engaged from the Square Kilometre Array. But it had been going for many years before that. As I said, it's been going for 20 or 30 years, a concept in some sense.
Mm. Financially, this is about double the size of your previous project, I think.
It's comparable. So if you look at the large telescope, the optical telescope project. So I was involved with an organisation in Europe called the European Southern Observatory. They're based in Munich. They've been going for about 60 years. They build telescopes and run observatories for the European research community in some sense. Their main facility is in Chile, in South America, because that's one of the best places in the world for optical telescopes. And they have been building basically €1 billion class projects. So the project I worked on mostly, which was in a place called Serra Paranal up in the Atacama Desert, it was 4 big telescopes all linked together, optical telescopes linked together, and that was about €1 billion worth of new investment in telescopes. And then they built another one after that, which was a radio telescope there, which is another €1 billion project. So these €1 billion projects in optical sort of domain have been around for a while. The Space Telescopes project, I was involved with the Hubble Space Telescope. That was a $6 billion project to build the Hubble Space Telescope. So that's the sort of numbers that get bandaged around. So we knew the SKA was going to be in the multi-billion-dollar range in some sense.
And what do you learn when you're working with multinationals, with various different companies? This large project that can get so confusing and so many arguments probably arise in its design, its construction and project management. What have you got out of that you can now bring to the SKA?
Tolerance. So you have to be a good tolerant person. So it was a really interesting learning curve to go into these kind of big international projects. So Hubble was interesting because I was inside NASA, and NASA basically solved all those problems for you in some sense. Then I went back to Australia and did some research work, and then went to this appointment in ESO in Munich. I was an astronomer. I was a researcher. I did research using supercomputers and looking at dark matter, and I wasn't managing budgets or running people or things. I was really just a research scientist in some sense. The very first day I arrived at ESO, I had to fire 3 people from my new division, and I had to approve a €1 million tender. Not having ever seen what a tender document looks like or having ever fired anybody, it was a bit of a shock to the system, right? So you have to learn quickly. You're thrown into the deep end, and to run a big project, to run a €1 billion class project, it requires lots of skills. And those skills are not part of the skills you learn to become a scientist in the classical education of a scientist. Okay, you learn how to solve equations, and you learn how to analyze data and write programs and things of this kind. So learning how to manage people, manage budgets, run projects, make decisions, that's all part of doing big science. So big science is these €1 billion sort of facilities, and you have to learn how to do that if you're going to be a scientist involved in this sort of game, right?
So were you when you first landed that job and you said you had this $1 million tender, and were you sort of furiously working away at night to try and figure out the financial situation, and, all these skills that you sort of you need to upskill yourself pretty quickly in that domain?
It was a bit of a shock to the system. Okay, I didn't really know what I didn't know, to be honest with you. I leaned upon more senior people there who had been through the mills, and I said, look, please help. I need to understand how this all works and how I'm going to do X, Y, and Z. Because I was having these amazing out-of-body experiences, right? There was this some room full of people like this, and this tender document comes by, and here's all the tender agreements and the contracts, and I was like up in the corner of the room watching down. I think, oh my God, what's... but you have to do it. You have to jump in and do it, and you can guide by the senior people. But it's having we were lucky in having an organisation that had done this many times, and so they were very good about kind of bringing you along and stuff like that. But it was a real revelation to me, because when you're in the academic world, when you're trained as a scientist, you're trained to produce scientific results and do publications and things like that. And if you're at a university in particular, your metrics, your judgment is purely on how many papers you produce and how much science you produce and things like that. If you spend some time, doing a management course or learning how to run people, you'd be considered to be a traitor or on the dark side or something, and you didn't produce any papers. Why did you waste your time doing something other than produce papers? And so the way scientists are judged, particularly by academic organisations like universities, was almost opposite to the sort of skill set you really needed to acquire to become part of a big project. So when I left Australia being a pure scientist and plunged into this other thing, I knew it was going to be a big hit to my research time, but I'd sort of figured out that was necessary to be able to be engaged in these big projects. And so even today, I still see young kids coming in doing their PhDs and things who think they're going to be able to sit at a desk and wear a white coat and solve equations all day. I tell them, look, you've got to take risks, you've got to change your path, you've got to learn things you don't think you should learn or don't want to learn, because big research, big science, big projects, which is what research is about today, to solve the hard problems, you've got to take these kinds of right-angle turns.
We try to teach that in STEM, but it's really hard to instill that belief that it's actually useful. We have to convince them that these are skills they need to have. I don't want to work with him. I don't want to solve my own problems. I just want you to tell me an equation to solve, and I'll do that. Yeah. How do you think we address that?
I think, for me at least, being part of the big project
and communication as well as a scientist, communication is obviously absolutely
exactly.
key.
You've got to learn how to communicate to all sorts of audiences. You can't just be talking to other scientists. You've got to talk to kids and to politicians, in particular politicians. Learning how to speak to them is a very important skill. You have to learn this stuff, and I guess you can't. It's hard to do it in abstraction. Or in other words, just teaching in a classroom is very hard. You have to be involved in an enterprise, a project as such. And so what we're trying to do is get our PhD students hooked into a large external project, whether it's with industry or whether it's with another scientific organisation. Get into it for 3 or 6 or 12 months. See what you need to do to be successful in that environment, because you can't instill the importance of this in people without a positive example of what you need to do.
Or an authentic example.
Yeah, so this sort of, we call it internship or immersion in an environment like that, I think is far more effective than just sitting up and listening to a lecture in a room, right?
Mm. Well, what about the fact, though, that you need people who have real hyper specializations in things to do the absolute most cutting edge sort of science? How do they, those scientists still have to just balance that with being able to communicate well with all these other skills you're talking about, and be very, very focused in a certain area?
They do. It is a balancing act. It's much more of we're teaching, I think, much more of a balancing act today than we have in the past. So when my organisation, for example, my institute, we're funded on a 5-year basis, okay? So if a new person comes into the organisation, say, look, you're here for 5 years, but if you want to stay for longer than 5 years, it's up to you to contribute to this organisation to put the basis of the next funding round in the place, and it goes on and goes on, be part of the project going forward. And so they quickly realised that to do that, you've got to do a bunch of jobs. You can't just do your research. Yes, publishing papers is very important, but I have to do education outreach. I have to go and talk to kids in the school. I have to manage a group of people to do a particular task. I have to run a little project to deliver some particular thing. So that's part of the training we give to our young career researchers in some sense, and that's essential. You can't, as I said, the old idea of a job for life in academia is gone long time ago. That's not what universities are about anymore. Nobody's going to give you a job for life. Maybe Harvard would, because it's got the endowment it can, but there are very few places in the world that will give you a job for life, because they say it's up to you to basically support your existence in this organisation, and to do that, research is critical, but so are a whole bunch of other things. Right?
So do you assume that they have knowledge of that before coming into uni, or do you think would you say no, you're not quite the person we're looking for because you don't have any of these skills?
I think when you look at the job ads, job descriptions, the critical, the job determining factors, we put all these things in there these days, right? So it's not just you've published all these papers, that's wonderful. You've got experience in this and this and this and this. It's in the job description. So we tell kids then, if you want to be successful at the next job, if you can demonstrate you've done, education outreach, project management, software engineering, research, or whatever, that's the kind of skill set we want to see. So we look for the kids who are, have some exposure to this. Obviously, coming straight out of universities, a lot of them don't, and you've got to train them up. So we give our kids media courses, for example, just teach them to sit down and talk to people like you guys in front of cameras, in front of mics. That's an absolutely essential skill, right? Because you've got to, as I said, you've got to be able to talk to the public, and particularly politicians. So we try to provide some of the training as well as the practical on training as well. But the job descriptions you will not see anymore. It just says you've published 10 papers, or you've had so much telescope time, or whatever it is. It's not the case.
So what else is required from students to get into a career in astronomy?
So, as I said before, I think passion is a prerequisite, in the sense that you must have an intrinsic passion for exploring, finding out, doing research. That has to be your driver. If you don't want to do research, then you won't become an astronomer in some sense, because that research is kind of the overarching passion that pushes you when times are tough, when the project's going belly up, or whatever it is. It's that passion for the answer. That's that passion of finding out that drives you on, right? So you've got to have that. You've got to have that passion to be a scientist.
Where do you get that? And this isn't necessarily your area of speciality, but we talk about this on a daily basis as teachers. Yeah. How do you get intrinsic motivation out of a student?
Look, I honestly think there has to be some seed of it, some germ of it there to begin with. I mean, can't
be taught.
I don't think it can be taught. I think from an early age, I was interested in science. I thought science was cool because you do lots of fun stuff with chemicals and God knows what. And then it slowly evolved into particular interests and particular passions about particular problems and particular individuals, excite you. Unless that's there, unless that, as I said, what Feynman called it the joy of finding out, unless that's in your soul, right, I don't think a research career is what you really are looking for, because a research career is hard. It's really hard. As I said, research jobs are almost always short term. They're very, very, very competitive, particularly if the research area is extremely interesting internationally. So you end up being a vagabond, a nomad going around the world, and 2 years here and 1 year there, and it's hard having a family. It's hard having a marriage. We've had, Kate was saying before, 17 houses in my married life so far. So it's not easy, right, to be a research scientist. Not at all easy. So you have to have that passion to drive you in the hard times to get you up there. And if you don't want to be a researcher, then great, go and do your bachelor's degree, go and do a master's degree, whatever it is, go out into industry, go out into teaching, go out into the the more applied kind of areas and do that. That's fantastically rewarding stuff. But research is a different thing. It's a very uncertain, a very demanding thing. So yes, it's, in the past there were, maybe as many astronomers as there were jobs. These days there are far more astronomy qualified people than there are jobs. So the astronomers are going out into all sorts of career paths, which is good because we do train them to do that. But you've got to have that passion. And I don't think you can teach that. I think it has to be there to begin with. And then once you've got the passion, as I said, that provides the motivation, I think, to take on some of these hard tasks, hard chores, hard times, to learn to go to the left and to the right in your career path. For a time, if the passion is the research that's driving you forward, you might say, gee whiz, I've got to stop doing my research for 3 years and do that job because that'll get me to that result. And that's hard, okay, really hard.
Yeah, the adaptability is something we talk about quite a bit as well. Being able to change paths and knowing when COVID's seen a lot of change, and I think people that have gone down certain pathways and can't change have been really restricted.
Exactly. No, I think you have to know. Sometimes it happens by accident. Things just present themselves. Sometimes it's very deliberate. But my experience is most of the time it's fairly random, actually. So things happen and think, okay, that's an interesting. I hadn't thought about that one, and maybe that's something I should be doing. Right?
And you were saying before that some of these projects can be almost half of your career in terms of time scale.
They can, yeah. So in the space-related areas, like, projects like Hubble took 20, 30, 40 years to kind of go from idea from the early 1970s all the way through to the end of the decade, end of the century. SKA is going to be 20 or 30 years. The VLT project I was working on in Chile was 20 years.
It's a very, very large telescope, isn't it?
Very large. Yeah, we don't have very good names in astronomy, as you know. Yeah. The next one after the VLT is the ELT.
Extremely large.
Extremely large telescope. Good. 10 points too. So no, you've got to be aware that these projects do take a large chunk of your career. So they are very demanding. They can be 2 or 3 of them in your career path, but usually there's lots of zigzaggies in those projects as well, from maybe the research side to the technical side to the management side to the leadership side to the education side.
Sounds quite varied.
It
but
is,
I wonder, we talk a lot about the instant gratification generation that want to have constant change in their careers. The thought of a 20-year job is probably quite foreign to a lot of younger kids.
Yeah, I think it's, as I said, it's not. There could be many jobs in that 20 years. It's all part of the same project. These big projects, as I just said, there's lots of roles to play, and you tend to migrate through them as you become more experienced. But it's a commitment to a particular result. That's just where we are right now.
Peter, can you give us some examples of the different kinds of roles that people have at ICRA? That some of our students might, if they're heading into this field potentially, the kind of things they could be doing.
So it's not what you call a classical research organisation. It wasn't set up that way. It was set up as an organisation to be very attuned to the needs of the SKA project, obviously. So if we want the SKA project to produce returns in Western Australia, we've got to make sure we've got the right people to do the right jobs. There are sort of 4 probably main areas of jobs. One, of course, is the science. You want to be able to use the telescope and at least define the science the telescope should be doing, and so understand the challenges and the problems, and so do the science. That's obviously a part of the job. The next one is the engineering. You need to be able to build or contribute to the building of the telescope, because you kind of have to understand the problem to be able to decide how to build it. Okay, so it's kind of that way around. What do you need to build to solve the problem? So the engineering and the scientists work very closely together, and so having them in the one organisation is fantastic. So we have engineers who are experts in radio technological engineering, antennae and amplifiers and all that sort of stuff. So we have those, and they can go out to the site and test out ideas and do things like that. So engineering is the second biggest part. The third part is data. This project's all about data. Data flow, data management, data processing, data visualization. Astronomy is a data-driven science. Since the 1980s, there's been more data than telescopes, if you know what I mean. The data is the dominant factor. And so you've got to be able to deal with the data. And so data scientists, data specialists, software engineers, programmers, they are critical to the ecosystem of the telescope as well. And last but not least, education outreach. Okay, you've got to be able to convince people you're doing a good thing. You've got to be able to communicate to people you're doing a good thing, and all sorts of people, kids, politicians, people in the street, the media. So those are the 4 big skill sets that you'll find inside ICRA. Okay, the science, the engineering, the data science, and the education outreach.
And in terms of the education outreach, is there a hell of a lot more in that space that needs to happen than people might think for you to stay sort of relevant in the minds of the public and send that message that you're trying to send?
So we have a 5-person team. Okay, we're a 200-person organisation, but there's 5 people who do the education outreach full time. This is a time in Australia when there's basically no more science journalism in the country. I mean, most of the newspapers have not got science journalists anymore, so that's a dying skill. So we're trying to grow it in terms of science communications and education. With social media, you have to have people who can do that, the Twitters and the Facebooks and the Instagrams. You have to have those sort of skill sets. You have to have the print and TV media people. You have to have the people who can talk to, as I said, to put up exhibitions, run events, go to schools, run things like Astrofest. Astrofest is 5,000 people every year. We have the world's, Southern Hemisphere's at least biggest astronomical festival here in Perth. So that's run by us. So you have to be able to run things like that, put presentations and stuff forward to politicians, visiting dignitaries. So it's a bizarre combination of education, protocol, social media, marketing, communications. It's that whole set.
Okay, I wouldn't mind pivoting now, if you don't mind, Steve, to some questions about what we actually might be able to find out through the SKA and the science that might get generated, and there's some of the kind of questions that it seeks to answer. Because I've got a few questions here from some students at Scotch, which I'd love to hit you with.
No, go for it.
Well, perhaps before I hit you with those student questions, could you tell me a little bit about some of the questions that you're most excited about that the SKA is hoping to answer?
Sure. So, like basically every telescope that's ever been invented, SKA has been built to answer particular questions. That was what it was designed to answer. Particular questions. It was designed to find the radiation, the energy, the light coming from the very first objects in the universe, which is a fantastic ambition. So that's its design thing, and it's going to do that in spades, we hope, right? It's also probably going to do stuff it wasn't meant to do, right? So every single telescope that I know about, all the big telescopes in the world, whether it's the old ones or the new ones, are almost always known for something that they weren't designed to do. They sort of found along the way. And so that serendipity, that discovery of the unexpected is really exciting, because that's makes the blood boil kind of thing. You find something that's, what the hell is
it how dark matter was discovered? Something along those lines?
Dark matter was...
Someone was looking at the rotation of far off galaxies and realised that it pulled in quicker than it should have.
It was a realisation that there was something wrong. Okay, so there was a guy called Fritz Zwicky, who was a Swiss, rather strange man, astronomer, who worked most of his life at Caltech in Pasadena. And he realised in the 1950s, actually, that if you looked at a cluster of galaxies, if you looked at the big, sometimes you have galaxies come in big, like swarms of bees. There's thousands of galaxies all in a big kind of group, and they all move around the centre of, they buzz around the centre of this sort of group. He realised back then that the galaxies were moving much faster than you would expect just from the light of the galaxy. If you took the light of the galaxy, the light's proportional to their mass. So if you figured out the mass of the cluster and you figured out what sort of velocity it should have, the galaxy seemed to be moving too fast. And so he was the first person to say, well, I think there's some missing mass. And he termed that term missing mass. That was back in the 50s. And so ever since then, people have found other situations in which there is missing mass. So
how did you prove light is proportional to mass?
So a star like the sun, it has a certain amount of light coming out of it, and it has a certain amount of hydrogen gas that glows to produce that light, right? So the more hydrogen gas you have, the more light you produce. The more burning you can have, right? So the bigger the star, the brighter it is in some sense. So there is a connection between the luminosity of a star and the mass of a star. So that's where in a galaxy, which is just a collection of stars, there's a connection between its luminosity and its mass. Okay. So people realized in the 70s that the rate at which stars were spinning around the middle of a galaxy was actually faster than you'd expect just from the light from the stars, because there was more mass there. And it was actually a guy called Ken Freeman, who was an ex-Scotch student, who was the first person to realize that the way that the stars were spinning around galaxies was completely different than what it should be.
He realised that.
He realised that. Yeah, Scotch student, yeah. So if you can predict, in other words, if you have a distribution of stars and they're all going around circles more or less, you can predict how the rotation velocity should change as a function of radius, right? So he predicted what that should be, and then he compared to the observations, and the observations showed that it was a completely different curve. It was, the whole rotation curve was different. So he said, well, there's obviously some dark matter, and he came up with the dark matter kind of idea. So Scotch is intimately connected to the dark matter story. But there were many people who kind of found evidence for this, that there was evidence, whether it was clusters of galaxies or spinning galaxies, or there's this amazing thing called gravitational lenses. Okay, so if you have a big bunch of matter and there's a galaxy on the far side of it, when the light comes through this big bunch of matter, it gets distorted, like kind of going through a lens, right? So sometimes you can see really distorted images of galaxies, and it's because they're on the far side of some big mass distribution. And when you figure out how much mass you need to distort the galaxy image so much, it turns out it's a hell of a lot more of the mass than it's in the cluster. So there's lots of evidence from different areas of the existence of dark matter around galaxies, and it's one of the, for me, that personally, that's a problem I've spent most of my career working on. I'm a computational astrophysicist, so I do, early in my career, I do lots of simulations with computers about how galaxies move and collide and how they get formed, and dark matter was all part of that story. And then I did a big project to actually go and look for dark matter, and we didn't find any, which was disappointing. So, I've been involved with the dark matter story for a long time.
We don't have an answer on that yet, though, really, do we?
Yes.
Has it progressed much since that time?
The evidence of its existence gets better, but we're continually frustrated about finding the silly stuff. All right, so it's 90% of the universe that we can't see, which is very frustrating. It's like the iceberg, right? We can see the top bit, but not the bottom bit. We kind of think we know. Let's just imagine what could it be, right? Just suppose so it's obviously got to be dark. It can't be shining stuff because we don't see anything shining. So like a dead star, for example. So a star, it goes through its life, it runs out of fuel, it turns off, goes black. Right, so a dead star is a good black thing. A rock, like the moon, it's black, it doesn't shine by itself. Subatomic particles, they don't shine either. They just run around little atoms all over the place. So let's try and look at how can we test if the dark matter is one of those things, whether it's a dead star, a rock, a particle. And so there are various experiments that have been run to look for dark matter in those forms, and I was involved with one of them, and found nothing. Couldn't detect it by clever methods. Couldn't detect. So in other words, we're running out of options. The only option that's really left is a thing called a WISP, which is extremely, extremely small atomic particle. It's probably the smallest thing we can even imagine. It turns out that these little wispy things, when they run through the galaxy and interact with the magnetic fields, and the galaxy has magnetic fields, it can sometimes go pop and turn into a photon. And it turns out those photons are energy in the radio. So in principle, radio telescopes might be able to detect this popping off of these little dark matter wisps, and so one of the things the SKA could do is find dark matter through that path. So we haven't run out of options completely, but it's getting a bit scary. We're kind of running out of options.
So what role does quantum physics play in how we can understand potentially dark matter?
So this last option in particular, this WISP option, is a prediction of the fundamental theory of particles, so quantum chromodynamics, so it's quantum field theory, which is the quantum theory of particles. Okay, so that they predict the existence of these very light particles, and in fact, when you go through the quantum calculations, it turns out the early universe probably produced very large numbers of these very light particles, and so maybe enough to make all of the dark matter in the universe. Right, so there's a hope that the universe, through basically a quantum process, produced a lot of its early mass in this form of these extremely small particles. Right? So we haven't given up the quest. We're still hunting. I hope, before I get to the end of my career, we've found the silly stuff. But it's one of those extremely interesting problems where it's there, it's important, it's had a fundamental impact on the way galaxies have evolved, how the whole universe has evolved, but it's just not you can't touch it, right?
So there's a possibility that the SKA may find something?
So it's if this radio signal from these very light particles is there, if that's what the dark matter is, then the SKA should be able to find it. Yeah, it's sensitive enough to do it. Okay.
All right, this might not be a question that necessarily concerns the SKA so much, but one of our students, a Year 5 student, Sebastian Fugel, has asked, how close are we to knowing much about the habitability of planets beyond our solar system?
That's a really good question. That's probably one of the most remarkable things that's happened in astronomy over the last 30 years or 40, through my academic career. When I was a young student, the sun had like 9 planets at that time, and then there were basically no other examples of planets anywhere else around, maybe 1 or 2, right? And so there's this famous equation called the Drake equation that predicts, extraterrestrial intelligence, and one of the terms of the equation is how many planets does typical stars have, and that number was almost always 0, right? Over the course of that 30 or 40 year period, techniques have evolved to actually measure indirectly the presence of planets around stars. And those experiments now have been incredibly successful. There's a satellite called Herschel, which has been surveying pretty much every single star in the Milky Way, and lo and behold, pretty much every single star has planets, right? So it's gone from, that term's gone from 0 to 1, right?
And is
so,
that determined by the star actually moving on a central axis?
Yeah, so there's a couple of techniques. One is the wobble,
Yep.
exactly right. So basically the star tends to move around because it's got planets around it. The other one is direct occultation, so basically a planet moves in front of a star.
Okay.
And blocks some light. So anyhow, we've gone from a complete revolution in some sense from thinking that most stars don't have planets at all to forming planets is absolutely normal part of star formation. So every single star that forms, if it doesn't form planets, there's something kind of weird, right? So there's 100,000 million stars in the Milky Way, so there's 100,000 million planetary systems. In those 100,000 million planetary systems, there is lots and lots of planets that are like the Earth. In other words, they're in the same location with respect to their star. Their star is very similar to the sun. And so habitable zone planets, we're finding lots of them. Right?
That seems like a lot of stars to observe. Are you using artificial intelligence or coding to try and help determine how many planets are around each star?
So we have this... We're lucky to have some very advanced satellites up there now. As I said, one particular one called Herschel, whose mission was just to basically look at a few 100,000 stars, right? It was going to look at every single one of those few 100,000 stars over the course of a 5 or 6 year mission and measure the wobble for every single one of them, right? So we've gone from having data on a handful of stars to 100,000, 200,000, maybe 1 million stars, right? So, and this telescope's amazing, right? So, our knowledge of this presence of some planets around stars has gone astronomically, orders of magnitude up.
Got another big question here for you. This one is, what is the universe is expanding into? You've probably heard this about.
This is from one of our old guests too, right?
It is. This is from a scholar in residence, Akram. He said, how do you conceptualise what the universe is expanding into?
If I had $1 for every time I get this question. Look, it's where analogies break down. Okay, so the analogy for the expanding universe that everybody uses is some sort of balloon, right? So you have a balloon, and you point dots on it, and you expand it, and all the dots move apart, and that's the galaxies moving apart as the universe expands. It's a good analogy. It communicates the right sort of physics in some sense. What it doesn't do, of course, is communicate what the universe is really like. The universe isn't a two-dimensional surface, which is a sphere. Right? That's just not what the universe is. Einstein, his work taught us that there was a very intimate connection between the mass of the universe and the energy of the universe. And so it turns out that the geometry, the shape of the universe is intimately connected to the mass in the universe, and it's described by the Einstein equations. So effectively, space is determined by where the mass is, and then the mass fills the space that it determines, right? So it's like a self-propagating kind of idea. So thinking about outside of that doesn't make any sense because there is no outside, right? So, because the only place where space exists is where the mass and energy exist. So there's no outside because there isn't any outside. Right, there's no space out there, right?
It's kind of a difficult thing to visualize.
So this is the problem. As I said, you think of try to think of an analogy of that. It's very, very hard to think of one. You can't use the balloon anymore because there's an outside the balloon and inside the balloon. but try to think a bit like the Einstein idea that, I said, mass and space and time are all intimately connected. Space, time, and energy and mass are all connected, and they all effectively, one creates the other. So it's like a connected loop. So you can't have one without the other in some sense.
And how do you explain the fact that the universe is expanding at an increasing rate?
So that was
given what we know about dark matter.
That was a surprise. Yeah, that was a real surprise. That was, in fact, Brian Schmidt, who's visited Scotch several times, won the Nobel Prize for that discovery. So it's a weird one. Okay, so we think the only force that's relevant to the universe is gravity. The only force that's long range and strong enough to affect the whole universe is gravity. Electromagnetism is very sort of effectively short range. It deals with atoms and things like that. Gravity is a long range, very weak but long range force, and it can mold the way galaxies move. So gravity, of course, is attractive force. It's not a repulsive force. So if you take a ball and throw it up, it goes up and up and up and eventually stops and falls back down. And we kind of had that picture for the universe, that the universe began with a big bang, it would go out and out and out and out and out, and maybe eventually it'll stop and perhaps even fall back down again, because gravity was always trying to pull it back together, right? Finding that the universe, for whatever reason, was accelerating into expansion means that there's something which is like anti-gravity or a pressure. Something was pushing it out. So where does this pressure come from? I mean, you can imagine if I gave you a box, right? And I told you the box was completely empty. There were no atoms, no molecules, nothing in it, perfect vacuum. And you pushed on the box and it sprang back. You'd be a bit surprised, right? So people, one of the analogies is invisible bed springs, like the whole universe is full of these invisible bed springs, and it just pushes, right? And we don't have a good idea. And that's good, okay? Because we know there are things missing in our theory, our picture for the universe. We know in this last century, in the 20th century and this century, we have two incredibly successful theories of the universe. We have the theory of quantum, the quantum theory, and Planck and these people, and we have the theory of gravity, Einstein's theory. So one describes the very large, one describes the very small. And they're both individually fantastically, you can test Einstein's theory to 14 decimal places. It works to 14 decimal places, right? Fantastic. When you try to describe the early universe, which is the Big Bang, when everything was basically compressed into a very small volume, so you've got the energy and gravity of the whole universe, but in the size of atoms, right? So you're trying to push the quantum theory and the gravity theory into the same place to work together. When you try to do that, it breaks. Both theories fail to describe that. You can't describe. People have been trying for years, including Einstein, tried to marry together these two ideas of quantum and gravity to describe the early universe, and it just fails. You just get 1/0. It doesn't work anymore.
And there's still attempts, isn't there, to
there's still
for
attempts
a unified
to
theory
do,
of everything.
But nobody's got there yet. Okay, This dark energy thing was a surprise. And a lot of people think that if we understand, but part of understanding that story is solving the quantum and the gravity story. The thing that's missing in that theory will help us understand the dark energy. Okay, so that's why discoveries are like Brian Schmidt's, are incredibly important, because they point to, look, you forgot about that thing. You didn't even. That's what telescopes. That's one of the things where telescopes discover things you don't expect. Right? Nobody expected expansion to accelerate. I mean, that's just crazy. But it does, and that tells you've missed something important.
So what are the implications for the way the SKA is able to find things out, given the fact that the universe is expanding at an accelerating rate? How does that impact the way that what the SKA can find? Is that going to...
So the SKA is critical to this story, and for the following reason. So the data that Brian Schmidt and his colleagues took on this expanding, accelerated expansion, it came from looking at fairly shallow into the universe. In other words, we are looking at maybe a 1/10 the way back to this first objects. So we know in that last 1/10 of the universe, there's evidence of this expansion, right? Question, has it always been there? In the other 9/10 of the universe, was it also accelerating? Was there some point in that 10/10 that it started and stopped expanding or being pushed? So part of the clues, or finding the clues to this dark energy, comes from understanding how this thing evolved over the cosmic history. And so you need to have a telescope that can give you the cosmic history story, and that's what SK is about.
It's amazing.
Who funds these kind of projects, the SKA, and do you have to get government funding?
So absolutely, well, you have to get multiple government fundings, which is where the fund starts.
Or is there any innovators or entrepreneurs that would like invest, depending on what possibilities and technologies come out?
Yeah, not at this level. There are entrepreneurs in the world, mostly in the US actually, who are willing to invest $100 million in a science project because they think it's fun or they think it's may give some technology. We're talking about multi-billion euro projects, and so nobody that I know of has done those privately. They've all come from government science budget investment, but these projects are all much bigger than any one country's science budget, so that's why you need a bunch of countries to gang together to do them collaboratively. So European Southern Observatory is 15 countries, been around for 60 years. It's what's called an intergovernmental organisation, so it's a treaty level thing like NATO and things like that. So they join together, the governments of those countries agree to put a whole bunch of money into a particular enterprise for a bunch of reasons, for a bunch of technical reasons and scientific reasons and commercial reasons. They all agree to do it. So you have to build these intergovernmental organisations, or intergovernmental agreements at least, to be able to do these big projects. And that's very hard. That's part of the skill set you need, you have to be like an international politician in some sense, not just talking to one government, but 15 governments. I mean, that's one of the other things I learned when I was at ESO, that you go to the council meetings, you've got 15 countries sitting around a table, all speaking different languages and different cultures and different ideas. You've got to get them all onto the same page and convince them that they're, if they're putting in €1 billion, they're getting their money's worth, right? So it's that management of those international relations is important to be able to do. And you're not going to do the big science without that. I mean, as I said, the kind of projects we run today are €1 billion, €2 billion. The space projects are going up to 6 and 7 and 8 and 10 billion euros. And
have you seen that political enthusiasm fluctuate much over your career as you've been trying to put these big projects together?
Yeah, I have. I think it's interesting. The SKA project's amazing in Australia. I'm talking about now. I've been involved with it for going on for 15 years now in Australia. We've been through multiple changes of government, both at the state level and the federal level, multiple changes of politicians and parties and prime ministers and science ministers. The support has continued all the way through. Okay, now why should that be the case? The reason is politicians, they're nice people mostly, and they're not interested in black holes or stars or galaxies. They're interested in economic returns and jobs and things like that. So one of the nice things about being involved in a big project like the SK is it has that ability to produce returns, to produce all sorts of returns, not just the science, but other kinds of returns as well. So governments understand that, they see that, they identify with it, whether it's diversifying the economy or growing new skill sets or starting a new industry or a new company or giving SMEs opportunities or whatever it happens to be. That motivates, political involvement and governmental involvement. So in Australia, it's been a fantastic success story in some sense. Internationally, it's been ups and downs. I think some countries at ESO, some countries came in, they also went out. They were, they were getting what they wanted, or they weren't getting what they wanted. So, it's an evolving story. But this one particular project, SK, has managed to attract this, at least in Australia, consistent interest.
But that's certainly not true for other big scientific projects that people have tried to get off the ground, right? I mean, there has been arguments out there saying that science funding has, not for the SK, but has dropped in other areas, in a lot of areas. Is that right?
And I think, yes, that's completely true. And I think some of that has been the lack of an ability to diversify the return. Okay, so that if you can demonstrate that, the people remain interested. But if you're just if you're just finding the Higgs boson, and that's all you want, and so what does politicians care about whether there's a Higgs boson or not, right? But CERN's been very successful at doing that because it's got so much spin-off and so much industry return and things like that. So, I think some projects probably haven't played that card strong enough in some sense, particularly early projects or young projects or projects that are just getting off the ground. They've really got to, scientists want to know what science is going to be done. That's fine, but you've got to be able to appeal to the broader returns. If you want to raise $1 billion, no matter where it is, you're going to have to appeal to that very broad return.
Okay. I think we're nearing the end. We've always got a couple of quickfire questions at the end that we're going to spring on you here, Peter, if you don't mind.
Sure.
This has been amazing, so we really, really appreciate you coming in tonight.
No,
it's fantastic. And thank you, Kate, for coming along as well.
Have we done okay?
Yeah. Do we get the tick of approval?
Absolutely. There are a couple of little things that Peter's left out, not you, like how many countries are involved in the SKA.
Yeah, that's okay.
That would be great.
We'll fill it in.
That's okay.
Okay. Well, we'll give you a chance to weave that in.
Yeah, sure.
Okay. Besides astronomy,
Yeah.
how do you relax?
Well, I like a glass of wine. I enjoy pretending I can play the guitar. I love photography, and I spend a lot of time in the bush with my cameras and taking photographs of birds. So, yeah.
What kind of guitar have you got?
I have a Gibson 339, which I bought myself for my 65th birthday, which I love,
That is a nice guitar.
and an old Matin, which is even better.
Oh, yeah, okay. You've got a maiden, haven't you?
I got
Maiden.
two, yeah. A mini Maiden and a 12-string.
No, I got
So-
a 6 Matin, and it's an oldie bit of goodie.
Yeah. So what are you playing at the moment on
I don't. I'm trying to become a.
We've actually got a guitar here.
Yeah, I'm trying to become a jazz guitarist, but that's a long ambition.
Well,
basically.
that's tough.
Yeah, it's tough.
Okay, Deserted Island, favourite album?
Pink Floyd Animals.
Mm.
Yeah.
Okay, Alex was, I believe, Blood on the Tracks, Bob Dylan from the late 60s. Okay, and what have we had lately? Queen?
We had a Ben Folds.
The Police,
Yeah.
Blood on the Tracks. That's a good one. Anyway,
Yeah.
we'll move on. What book or books has had the most profound impact on you?
In my young days, there was a guy called George Gamow, Gamow, a Russian physicist, who wrote a bunch of books called Mr. Tompkins in paperback, and they were basically books for young people to understand quantum mechanics and science, and he painted it, he wrote it, he talked about it without equations of any kind. He just talked about as if the quantum world was a big world and you could explore it. He was an incredibly gifted writer and a scientist who knew what he was talking about, so I was very motivated in my young days by George Gamow and his books. Later on, Jacob Bronowski. I was a very big fan of The Ascent of Man. I thought The Ascent of Man was one of the best things I've ever read. And it excited me about that journey of discovery, journey of knowledge. And so I still have a paperback copy of The Ascent of Man on my desk.
Oh, wow. Okay. Okay, what has been the biggest challenge you've faced in your career?
I think having the courage to change things. I think being able to sort of realize that I needed to learn new things and do things that I wasn't trained to do, or I'd been told if I did them I would be a failure, right? So, you know, when we were in Australia at Mount Stromlo, when I was still a real scientist doing dark matter stuff, I said, I'm going to go, I don't like this, you know, I'm going to go off to ESO and learn how to build big telescopes. And a lot of people said, you're mad, right? You're leaving the subject, you're going to be a failure, right? So that was hard to take. It was hard to hear, but I realized that, you know, that's kind of where I needed to go. So that was challenging. Yeah.
Okay, change. Yep.
Yeah.
One more.
Yeah.
What habit have you formed in the last 5 years that's been most beneficial to you?
Whether it's a habit or not, I think listening better than I've listened before, particularly to people, and then making decisions. Okay, I think a lot of people avoid decisions, and that's tough. I think that's not a good.
It's kind of still a decision anyway, isn't it? Really?
Yeah, I had the fortune. I was very fortunate to have a guy be my boss twice. His name was Riccardo Giacconi. He won the Nobel Prize for Physics. He was my boss at Space Telescope and my boss at ESO. And he gave me a few life lessons, okay? And one was don't avoid decisions, make them. With a bit of luck, you'll be right half the time. So that was good advice. So I'm right half the time at least. The other thing he gave me was early to bed, early to rise, work hard and advertise.
Okay,
Right.
fantastic.
And I think that's also a good life lesson as well. So yeah, so those are I think listening and making decisions, I think is a habit that I probably have learnt and tried to adopt very, very actively. Yeah.
Well, we better
All
ask
right.
Kate's question as well. How many countries are involved with SKA?
Yeah, well, there you go. How many countries involved?
14?
Yeah, it fluctuates a bit. Okay, 15 at the moment. It could be up to 17 if we play our cards right. But yeah, about that. Yeah.
All right,
Yeah.
Peter. Is there anything else before we finish that you wanted to share with particularly our students here at Scotch?
Yeah.
Before we go.
Sure. I think one thing I wanted to talk a little bit about was how important. So when you're trying to convince people what you're doing is impactful and important. Okay. And so that yes, the science of the SK is impactful and important, but it's also the other things that the challenges we have to face and meet during doing that, and how that it benefits society more broadly. Yes, astronomy is fantastic. It excites kids. It excites also, so it's intrinsically good. We've had 2 examples now with the skills that we've developed for the SKA, producing stuff which has nothing to do with the SKA, which is, I think, incredibly impactful for science. Okay, so let me give you one example. We had to, our engineering team, our astrophotonics team, had to invent a way of sending signals from the central computer of the SKA all the way out to the dishes and back again, over fibre optics. And these fibre optics are 1,000 kilometres long in some cases, right? So as you send signals over these cables, they're out in the sun and they get bent, and there's lizards walk over them and things. And so you have to correct the signal in very clever ways to make sure it stays stable and correct. So they invented the system to make the signal stable and correct over these long distances. And that's going to get built into the SKA. So great. Turns out the system that they've invented for this is exactly the system you need if you wanted to send a laser beam, say, from the Earth to a satellite in orbit. As you send a laser beam from the Earth's surface to a satellite, it goes through the air, and it gets twisted by the air, of course. And so by the time it gets to the satellite, it's all messed up. So you have to correct it. So their system they invented for the SKA is now applicable to sending laser beams to satellites. Why would you want to send a laser beam to the satellite? Answer: if you want to send a very large amount of data from a satellite to the ground, or from the ground to a satellite, radio is very limited. That's what we use right now. If you send it optically with a laser beam, you can send about probably 1,000 times more data. So if you want HD television of the first woman on the moon, you need a laser beam to send the signal to the Earth. And so we've invented the system to do that.
Oh, wow. That is incredible.
Right.
So that's that, and that's clearly going to be an incredibly
absolutely
commercialised product.
So we're now working on a prototype optical ground station network in Australia. So we're telescopes that send laser beams to satellites. One of them here in Perth on the roof of the physics building very soon, and that's an example of translating the skill sets that we develop by doing these big astronomy projects to other areas of society. So, this is part of what the Apollo program did it, going back to Apollo again. That they did it. We will continue to do it. These big science projects are not just about the science. They're about all sorts of challenges that need to get solved, and those challenges are very often applicable to all sorts of interesting problems, like this problem of sending lots and lots of data up and down to the sky.
Has that been commercialised?
On the verge.
Yeah.
On the verge. I can't talk about very much.
Okay.
but we have several companies we're working with who are going to commercialise this system, and Australia will be one of the leading optical ground station network players in the world. And as I said, we've got a contract in fact, 2 weeks ago, we got the first contract from the Australian Space Agency, from NASA, via the Australian Space Agency, to develop support for the Artemis project. So we're now supporting the Artemis project.
Wow,
that is incredible.
So
have you met Elon Musk?
No, I haven't.
But he could come knocking.
He could come knocking, yeah. So the kids to understand, it's not. Yes, it's about the astronomy, but it's about lots of other interesting stuff as well.
I noticed on the ICRA website, one of your team, gentleman's in charge of translation. Is that what you're referring to? Or is that a different kind of translation?
That's translation, yeah. So there's a translation program is exactly this program. So taking the skills that we have and translating into other areas. There's a whole bunch of interesting ones, and it covers all the way from ocean waves and petrol tankers to honeybees. You know, all those different areas have problems that they're trying to solve, where we're finding ways to translate the SKA skill set into solving problems in those spaces. Yeah.
Oh, that sounds like a really interesting job.
Incredible.
Yeah, it's good fun. So the translation managers has a lot of fun. Yes.
Yeah, I can imagine.
Yeah.
Okay, Peter, thank you so much for coming
Pleasure.
into the Range project and coming into Scotch. And we also have to another big shout out to Kate. Thank you so much for
allowing
arranging
me
this for us. Yeah,
No, my pleasure. Really love talking to you.
that was
Great
fantastic.
conversation. Thank you.
Thank you.